Okay, let's go ahead and take a look at today's lecture. We are continuing on, and now it's week 4. So I posted grades for the midterm exam. I believe you should be able to see them. And if you have any questions, so I don't return the exams, but if you want to see your exam, you want to see what questions you got right or wrong, feel free to stop by office hours anytime, and you can look over it, and I can answer any questions that you have about it as well. But yeah, now we are in the second half of the course. We are continuing on. So 1 week ago, prior to the midterm exam, I introduced probability distributions. We looked at the normal distribution, the binomial distribution, and we said, we learned how to calculate probabilities based on that. Okay, and this all fits in part of the big picture of statistics, in that we are trying to learn about probability. When we learn probability, we learn about randomness, and we can start to distinguish between what is possible by random chance versus what is not really, what's unlikely to happen by random chance. And so that's because ultimately we want to be able to decide if there actually is an association in our data, or if it's just a random fluke. Okay, and so we are trying to learn, distinguish between what could happen under randomness versus what couldn't, and so today's lesson fits into that part of learning about probability. All right, so this is kind of where we've been so far, and this is where we are starting this week. So today, so in the first half, we covered 6 chapters, and then in kind of the rest of the course, we're just going to look at 3 chapters. Okay, we're going to cover chapter 7 today, and then on Wednesday we'll look at chapter 8, and we'll spend 2 lectures on chapter 8, and then we'll spend 2 lectures on chapter 9. Okay, and that will be it. And then at the end of week 6, you'll have your final exam. So chapter 8 and chapter 9, in my opinion, are a little bit heavier in content, and that's why I want to spend a little bit more time going through those chapters, rather than trying to compress multiple chapters every week. Okay, and just to kind of show you the roadmap of where we are, the first couple weeks we learned about describing statistics, descriptive statistics, describing our data with pictures, summary statistics, numeric summaries. We learned how to kind of describe all of that. And then we started learning the probability rules, probabilities of events, probability distributions last week. And today, this is where we are, sampling distributions. Okay? And so we're going to cover sampling distributions today. And I will introduce the very first kind of tool of statistical inference today, and that's going to be the confidence interval. And the rest of the course will all be about statistical inference. Chapters 8 and chapters 9, chapter 8 and 9 are all about statistical inference. First, we look at statistical inference for categorical variables, and then we'll look at statistical inference for numeric variables. And that's pretty much it for the rest of our course, as we're going to focus on statistical inference. But I would argue that's kind of the heart of our class. Okay. All right. So just to recap, a lot of the ideas that we're dealing with are centered around the idea of working with samples and sampling distributions. Okay. So we've got sampling terminology, and then we'll look at sampling distributions. And there's a kind of this mathematical principle, the central limit theorem, that applies to all of this. And once we kind of establish that, we can delve into our first bit of statistical inference, the confidence interval. All right, so once again, the whole point of all of this is that we are trying to make conclusions about the population. Right? We have some kind of question, and we want to figure out the answer to that question. And the population is everyone who's relevant to answering this research question, right? Maybe we want to know, what proportion of voters support, proposition, 246, okay? And, it's some policy or whatever, who knows, okay? And so, the population there will be everybody who votes on election day. That's going to be the actual population. But prior to election day, we want to kind of get an idea of whether or not, Prop 246 is going to pass or not. And so news organizations might do surveys, different public opinion research firms might try to do some surveys and do some polling to try to guess, okay? And the issue is that the population, that is, all the voters who are going to vote, there's just too many. There's just too many for us to try to survey until actual election day, right? And elections are costly affairs. They, it's important that we have, free and fair elections for democracy, but it's also very expensive, right? You have to have all of these poll workers. You have to have all of these machines. You have to be able to kind of count all of these ballots and everything like that. You need some kind of, basically the logistical setup of sending out ballots, collecting the ballots, making sure everyone who's voting is, properly registered and qualified to vote, and, nobody's voting. There's a lot of kind of work to kind of make sure that elections are being done properly, and so it's expensive, and so we don't want to waste too many resources to try to count everybody every single time, right? So if we are a news organization and we're not trying to get the final result that's going to determine public policy, and we just kind of want to get an idea of whether something will pass or not, we survey a sample. We select just a random selection of people, okay? And that's the sample. The sample is a selection of people taken from the population. Ideally, we want the sample to be representative. And based on what we see in the sample, we try to make conclusions about the population. Anytime, a lot of times we're going to be talking about summary statistics or numeric summaries about the population or about the sample. So we might talk about the mean of the population. What is the average height of everyone in the population? But we also might talk about the mean of the sample, right? You surveyed 50 people. What is the average height of your 50 people? Okay. Or maybe we're talking about the proportion in the population. What proportion of all voters support Prop XYZ versus the proportion in your sample, which is you surveyed 200 people, and what proportion in your sample of 200 people support Prop XYZ. And so in order to distinguish between summaries of populations and summaries of samples, we have two different terms. The parameter is a summary for the population, and the statistic is a summary of the sample. And statistical inference is the process of using a sample's statistic, that is the value that you get from your sample, in order to make conclusions about the population parameter. So we're using the statistic to learn about the parameter. So here is an example. A news organization or whatever, they do some kind of political poll, political survey. They survey a sample. They select 800 likely voters. The corresponding population would be all likely voters, right? and the sample has this statistic, okay? You get 44% of the 800 people you surveyed say they support candidate John Q. Public, right? So imagine some kind of, I don't know, there's some kind of primary or some kind of, election coming up, whatever, who knows, okay? 44% in your sample support John Q. Public, and the question is, okay, well, what proportion of all voters support John Q. Public, right? Does John Q. Public have a chance of winning, or is this person doomed to fail in the population on the actual election day? That's kind of the question, we want to go after. Okay, here's another example of statistical inference. All right, so here we could say, all right, let's say we get 50 volunteers. We needed people with high blood pressure. We find 50 people with high blood pressure, and they volunteer to be part of our experiment. The corresponding population will be everybody who has high blood pressure. Okay, and in our experiment, we assign half of the people to get placebo, half of the people to get the actual medication. All right, and at the end of the experiment, let's say we observe this data, this statistics from our actual sample. Okay, we get the mean blood pressure of patients who got the medication to be 125. The mean blood pressure of patients who got the placebo is 135. And therefore, the difference between placebo and medication is 10 millimeters of mercury, right? So you get 10-point difference between these two things. And so now the question is, okay, what does this say about the population? If we gave everyone in the population placebo versus everyone got the actual experimental medication, are we also going to see a 10-point difference between those two numbers, or is the actual difference more or less? Is there even an actual difference? Is it possible that we got this 10-point difference just kind of by random coincidence? That's kind of what we want to ask. So, as far as this class goes, we'll learn how to do statistical inference for categorical variables with proportions, and we'll learn statistical inference for numeric variables using means. There are far more statistical inference methods. You can do categorical variables, using the counts directly. You can deal with ratios, and there's all kinds of statistical tests that you can learn. We're just going to learn, kind of focus on these two types. And the two tools that we will also use will be the confidence interval and the hypothesis test. We'll learn two types of hypothesis tests, the z-test and the t-test, but that's about it. Okay, this is an intro class, so we're just learning some of the basic tools. And again, if you take an interest to this, you could take more statistics courses, and you'll learn more statistical inference methods and things like that. Okay. I said we have we have parameters and we have statistics, and to kind of help us keep track of these different things, we have different symbols. So anytime you're dealing, so with statistics, you've got the mean, x bar. When you're dealing with the population, the parameter for the mean is this Greek letter mu. The standard deviation of your sample is s. The standard deviation of your population is the Greek letter sigma. The proportion of your sample is p hat. This little cap over the p is the hat. And the proportion for the population is just p. Okay, so these are kind of our symbols that we use. And today's lecture will focus on the proportions. P for the population and p hat when we're dealing with a sample. All right, let me go ahead and give you your first view quiz answer for today. First view quiz answer is the letter B. B as in bear. B as in bear is the first view quiz answer. We've already covered this, but here it is just for reference, is that sampling is the process selecting individuals from the population to be part of our sample. If a method that should produce a representative sample is simple random sampling, but it's not guaranteed to produce a representative sample. And if you get a sample that's not representative, then your sample is said to be biased. Okay, if you select too many or too few from any particular group of people, then you have a biased sample. All right, this brings us to this very important concept of a sampling distribution. And so if we do random sampling, okay, random sampling, and random sampling could be as simple as repeating a random trial a bunch of times. That counts as a random sample. Or it could be actually selecting people at random, okay? So anyway, let's say you select a random sample. Let's say we have the same research question. What proportion of people support, are going to vote yes for some upcoming proposition, right? So we'll call it proposition XYZ. What proportion of people are going to vote yes for this thing? And so you and I, let's say we're both interested in the same question, and we decide to survey people. You go out and you somehow get a random sample, and you select people. And then I go out and I also get a random sample, and I ask them the same questions. Okay, and we're both trying to work with good intent. We're following the process. The thing is because your sample is random and my sample is random, okay, what we get in our samples, we expect to be similar, but not necessarily exactly the same, right? You survey 100 people, maybe 45 of them say, yes, I will vote yes on this proposition. Okay, I survey 100 people, and maybe I get 52 people who say, yes, I will vote for yes, right? And so I'm getting 52%, I go, oh, it's going to pass, all right? You get 45%, and you say, oh, it's less than half. It doesn't have majority support, right? Who's right? Who's wrong? Okay? And the answer isn't that one of us is right and one of us is wrong. That's just what happens when you do random sampling. Because it's a random selection, you don't necessarily get the exact same values, right? So sample statistics will vary from one sample to another sample, right? That's a very important concept, is that because it's random sampling, even if we do everything correctly, we're not going to get the same exact value every single time, right? And so, if we're dealing with a categorical variable, we're looking at the sample proportion. And when we get the sample proportion, all right, whatever number we get, we expect it to be close to, but not necessarily exactly equal to the population proportion, right? So the entire population, there's some number, okay? On election day, the proposition will either pass or fail with, a certain percentage of yes votes. That's the parameter that we want to try to guess or figure out by doing samples, okay? Some polling before. But whenever we do a random sample, we expect our sample proportion to be close, but not necessarily exactly equal to it, right? I mean, just a simple example, if you flip a coin, we know the true probability of this coin landing heads in the long run is 50%, okay, right? But let's say you flip the coin 100 times. Are you going to necessarily get exactly 50 heads and 50 tails? Not necessarily exactly that, right? Maybe you get 51 heads and 49 tails. Maybe you get 49 heads and 51 tails. Maybe you might even get like 45 heads or 40 heads or something like that, right? And so just think about this and just kind of intuitively, what could happen when you flip a coin 100 times? So if we flip a coin 100 times, let's say this is a fair coin. So in the long run, it's going to be 50% heads. But if you flip it 100 times, could you get, is it possible where you only get 45 heads. Your proportion is 45 heads out of 100 flips. Could that happen? And I think we would agree, yeah, that sounds like it could happen, right? That seems very likely. You're not going to get that every single time, but could it happen? Sure. That doesn't seem all that weird, okay? What about getting only 40 heads? If you have a fair coin, is it possible to just get 40 heads out of 100 flips? What do you guys think? Okay, and I would say yes, but certainly 40 heads seems like a less likely outcome than getting 45 heads, right? Sounds like, okay, 45 heads out of 100 flips, that sounds reasonable. 40 heads, okay, that's a little bit tougher sell a little bit, but sure, that could happen. What about 35% heads? So we're getting it 35 heads, 65 tails. Could that happen by random chance? It could. It's not impossible, but again, that seems more unlikely. Okay. What about, again, fair coin, we're flipping it 100 times. Could we get 25 heads, 75 tails? So theoretically, it's not impossible, but how often do you think that's going to happen? 25 heads, 75 tails, 100 flips. Fair coin. Okay. It's not impossible. Theoretically, it is possible, but it seems very unlikely, right? Okay. What about, again, flipping a fair coin 100 times? Is it possible by random chance you get one head and 99 tails? Okay, so again, theoretically, it's not impossible. Like if you flip the coin 100 times and you do this, like, you know, for all of eternity, it might happen, but it's incredibly unlikely. So unlikely that we can practically ignore this outcome, right? Like the idea of getting one head and 99 tails with a fair coin just doesn't seem like a realistic thing to happen, okay? And so here's kind of the bottom line. All of these things are theoretically possible, but intuitively we know that some of these things just are very unlikely to happen, okay? We're very unlikely to witness this. And so if we do, witness something like this, I think we would start to question whether or not the coin was even fair in the first place, right? If somebody says, I flipped a coin 100 times and I got one head and 99 tails, man, I got some really lucky result. I think we would say, I don't think you got that by random chance, by random luck. I think something went wrong. Something went wrong while you were flipping the coin, okay? Maybe the way you're flipping the coin, I don't know, whatever happened, okay? It just doesn't seem right, okay? So this brings us to the sampling distribution. The sampling distribution is the distribution of the different possible sample statistics that we could get, right? So a sampling distribution shows us the probability that a random sample of a given size produces a particular value of the sample statistic, okay? We'll take a look at the sampling distribution for the sample proportion p hat. So we're going to look at the sampling distribution of p hat, and then in chapter 9, so we start with chapter 7 and chapter 8 dealing with proportions, and then in chapter 9 we'll deal with the sampling distribution of the mean, the sampling distribution of x bar. Okay, so we could figure out the sampling distribution of p hat because we've learned the binomial distribution, right? So we could say, all right, if I flip the coin 100 times, so if my n is 100 times and I'm using a fair coin, so my p is equal to 0.5, I could say what's the probability the coin lands heads exactly 50 times out of 100, okay? 50 times out of 100, the answer to that is the binomial 100 choose 50, 0.5 to the 50, 1 minus 0.5 to the 100 minus 50, or also 50, okay? And using the computer, I could just do d by gnome 50, 100.5. And this is the probability of getting 50 heads out of 100 flips, or the probability that my sample proportion is 50%, okay, 0.5, right? So I just want to make sure this part is okay, that the probability that p hat is equal to 0.5 is equivalent to the probability that x is equal to 50 here, right? When n is 100 and the probability of getting heads is 0.5, okay? So here we get 0.07959, so just a tiny bit under 8% probability. Okay, and I could go through and I could calculate, all right, well, what's the probability of getting a proportion of 49%, right? Getting 50% proportion of 0.5 is 0.07959. The proportion of getting 49% heads, or 49 out of 100 flips, is going to be 0.07803, so just ever so slightly different, but just a tiny bit lower. And I can go through and I can calculate the probability of getting every single one of these results. What's the probability I get only 1 head, or 2 heads, or 3 heads, or in our case, I guess 1%, 2%, so on and so forth. And here I kind of have them all kind of listed out here. Not to worry. Here's the plot. This is the plot of the sampling distribution, right? So what do we see? We see, so this is a probability distribution, or sampling distribution of p hat. We see, okay, the most likely outcome is I flip the coin 100 times and it lands heads 50% of the time. And the 0.5, that line is the tallest right here. But also likely is 49% heads. Okay, it's just a tiny bit shorter. And 51% heads is also pretty likely. These bars next to it are just ever so slightly different from 50%. Okay, 48% heads and 52% heads is not too far different. And we could see as that number goes lower, so 49, 48, 47, 46, 45% heads. 45% heads is, you know, not unlikely, but it's less probable than getting 50% heads, okay? And the farther I go away, 44, 43, 42, 41, 40% heads, right? What's the probability I flip the coin 100 times and I get 40% heads? This number is a lot lower, okay? This number is, you know, it's half as likely, less than half as likely as getting 50% heads, okay? 40% heads. And same with kind of the flip side of getting 60% heads. And the farther we go, okay, so this is 40% heads, what's the probability, you know, by the time I get to say 35% heads, look how low this line is, okay? This is saying it's, again, not impossible, but it's very unlikely. Look how short that bar is. It's very small, okay? 30% heads, it's practically zero at this point, okay? It's not, again, it's not zero. It's not, there's zero probability this is going to happen, but it's a very, very, very small and unlikely probability. And so you can just kind of barely see any dots to kind of indicate that there's a value there, okay? Does this kind of make sense as what this sampling distribution represents? It's the idea of, you know, if we flip the coin 100 times and I calculate the proportion of heads that I get, what values will I get for p hat? And we see 50% is most likely. Values higher or lower could happen, but as we get, you know, much above 50%, say, you know, 67%, 80%, those values practically become zero. Incredibly unlikely for those outcomes. So I wrote, the plot confirms what we know intuitively in that samples where your proportion is 50% are most likely, and it's less likely to get values of p hat that are far away from 0.5. And what we also see is that this thing looks a lot like the normal distribution. And we'll come back to that later. All right, so this, or I guess we'll come back to this normal distribution idea right now. We can kind of put all of this together in what's called the central limit theorem. Central limit theorem says that this distribution of p hat we can approximate it using the normal distribution. Okay, we can approximate it using the normal distribution. There's certain conditions that apply, but if we do use the normal distribution, then the normal distribution, you need a mean, you need a standard deviation. So what value do you use for the mean? You're going to use the proportion population, P. That's going to be your mean. What's the value for your standard deviation? It's this formula, the square root of P times 1 minus P divided by N. Okay? So we're going to have the standard deviation square root of P times 1 minus P over N. And that quantity is known as the standard error. The standard error is the standard deviation of the sampling distribution. So if we have n equals to 100 and our proportion is 0.5, then our sampling distribution of p hat can be approximated with a normal distribution. The center, the mean, is 0.5, and the standard error, the standard deviation, is the square root of 0.5 times 0.5 divided by 100. You take the square root of this and you get 0.05. So you have the mean of 0.5, standard deviation of 0.05, and that's going to be our normal distribution. So here I've overlaid a normal distribution where the mean is 0.5 and standard deviation is 0.05, and so the dotted line, remember the normal distribution is continuous, whereas this distribution, it's actually discrete, okay? In that we can get 50% heads or 51% heads, but you can't get like 51.513 or 0.5167, okay? Whereas the normal distribution is continuous and you can get kind of any of these decimal values. But anyway, what we see is that there's the alignment between the vertical lines and the dotted lines are like exactly the same. So there's like perfect alignment there, and yeah, so the normal distribution does a very good job of approximating the sampling distribution. Okay. All right, so what would happen? What would happen if we flip the coin only 50 times? What will the sampling distribution look like? What will happen if we flip the coin only 50 times? Okay, well, let's use the central limit theorem. The central limit theorem again says the mean is equal to the proportion P. So the mean is still 0.5. What happens to my standard error? The standard error is the square root of P times 1 minus P over N. So I got 0.5 times 0.5. This time I'm only dividing by 50 instead of 100. My N is half as much. So in my standard error, I'm dividing by 50. So that means my standard error is bigger, right? With a smaller sample size, my standard deviation, my standard error goes up. So when N was 100, my standard error was 5%. With N equal to 50, my standard error is around 7%. So what does it mean for the standard error to go up? It means our sampling distribution gets wider. So here it is for 100. It's centered at 0.5, but this is how wide the sampling distribution is. When I center it at, when I have N equal to 50, it's still centered at 0.5, but the distribution is wider now. The distribution is wider, all right? And that's because my standard deviation is bigger. Now, not only is it wider, but we also see the lines themselves are spread out. All right, and so what's going on here? If you look at this, the lines, you have a line at 0.5, you have a line at 0.52, 0.54, 0.56, 0.58, and 0.6. But you don't have a line at, say, 0.51, and you don't have a line at 0.49. You only have it at like 48% or 50%, okay? And why is that? Well, with N equal to 50, it's possible to get 48%, it's possible to get 46% heads, but it's not possible to get 47% heads, right? Because when you flip the coin 50 times, It can land 25 times heads, and that would be 50% heads. It could land 24 times heads. Heads 24 times. 24 divided by 50 is 48% heads. It could land head 23 times, and that would be a sample proportion of 46%, right? 23 over 50 would be 46%. But if you flip the coin 50 times, you can't get 23 and a half heads, right? You're either going to get 23 heads or 24 heads. So your proportion of heads is only going to be 46% or 48%. Okay, so that's why we only have lines at 46% and 48%. We don't have a line at 47% because it's not possible to get 47% heads with 50 flips. Okay, so as we change our sample size n, our distribution will not only change width, but the spacing of the lines will also change because only certain proportions of p hat will be possible. Okay. All right, so this is the distribution with n equal to 50, and I just want to show you what happens as I shrink the n. Okay, so if I shrink the n, notice what happens to the distribution. N equals 40, it gets wider. My standard deviation is 0.079. N equal to 30, it gets even wider. The standard deviation is 0.09. And here's n equal to 20. Standard deviation is now 11%. At n equal to 15, standard deviation is around 13%. And n equal to 10, the standard deviation is around 0.158. Okay, and with n equal to 8, the standard deviation is even wider, right? So notice with n equal to 10, I have a vertical line at 0.5, 0.6, 0.7. And so we kind of compare this, right? So over here, I said, if I flip the coin 100 times, could I get only 30% heads? And the answer was, okay, while it's not impossible to get 30% heads, the probability of getting 30% heads is practically zero. Okay, but with n equal to only 10, could I get 30% heads? Right? And the answer is, oh yeah, that could happen, right? Because if you think about it, flipping the coin 10 times, to get 30% heads, you need to get 3 heads and 7 tails. Okay, 3 heads and 7 tails doesn't seem all that weird of an outcome when you flip the coin 10 times. Okay, but if you flip the coin 100 times, to get 30% heads, you need 30 heads and 70 tails. Okay, 30 heads and 70 tails feels like a lot more unlikely to happen. Okay, so that's why our sampling distribution for 0.3 here is practically 0 when with 100 flips. And then with n equal to 10, the sampling distribution of getting 0.3 is is not that unusual. Okay, it's not quite 0. We do see there's a little bit of misalignment between the dotted line and the vertical lines, but it's still pretty good. Okay, and with n equal to 8, we have it's even more spread out. Okay, standard deviation is even wider. All right, does this kind of conceptually make sense? What's going on here with our sampling distribution? Right. So here's kind of my commentary. As the sample size n decreases, the spread of the sampling distribution increases. Okay. So I wrote this. I think makes intuitive sense. If we flip the coin 100 times, we would be surprised to get a proportion of 0.3. And if we flip the coin 10 times, we would not be that surprised to get a proportion of 0.3. Okay? And if n gets too low, the vertical lines don't quite match the dotted line. All right, what happens if we change p? What if we, instead of p is 0.5, what if we have some kind of special coin where in the long run it lands head 60% of the time? Okay? What does our sampling distribution look like then? Okay, well now the mean shifts to equal p. The center is going to be at 0.6, and our standard deviation also changes a little bit. Okay, so here it is, the sampling distribution when p is equal to 0.6. If I change it to p equal to 0.7, the distribution just shifts to the right. At 0.8, it shifts even more to the right. 0.9, it shifts further. 0.95, it shifts even further, right? At 0.95, we get, we start seeing some artifacting in that. What happens here, okay? If you have a special coin that lands heads 95% of the time, and you're flipping the coin 50 times, okay, you could get 96%, 98, even 100% heads, but you can't go any further to the right, right? You can't get 102% or 104% heads or anything like that. And so it kind of gets truncated over here. So we see, slightly a little bit of a mismatch there, okay? And here, if you have a special coin that lands 97% of the time heads, okay, you get something that looks like this, right? Going in the opposite way, here we got p equal to 0.5, 0.4, 0.3, 0.2, 0.1, 0.05, 0.03. Basically, it just kind of shifts the center of our sampling distribution. So as our value p changes, the center of the sampling distribution shifts. The sampling distribution kind of slides up and down so that the center is going to be at p. When p gets too close to the edge, okay, we see that the line and the dotted lines don't line up quite well, okay? Doesn't do a good job. All right, so we summarize all of this together in the central limit theorem. That is to say that the sampling distribution of our proportion p hat can be approximated with a normal distribution. Okay, the mean is equal to p, the proportion, and the standard error is the square root of p times 1 minus p over n. That's going to be the standard error. There's a couple conditions for us to use the central limit theorem, and that is, first of all, our sample has to be large enough. And we're going to say what size we need for the sample, n. It depends on the proportion p. So what we need is n times p to be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10. Okay? So both of those things, the n has to be large enough so both of these numbers are greater than or equal to 10. Our samples need to be selected randomly, so that's important. And then the probability p needs to remain constant for everybody, and part of that is you don't want to sample too much. The population needs to be big compared to your sample. So you don't want to sample over 10% of your population, or that your population needs to be at least 10 times bigger than your sample. Okay, so let's try applying this, okay? Let's try an example. Let's say I flip a coin 50 times, and the question is, what's the, what's the probability, if you flip the coin 50 times, what's the probability you get a proportion of 60% or more? Okay, what's the probability that's going to happen? So we want to know what's the probability that p hat ends up being greater than or equal to 60% if we flip the coin 50 times. Okay, well, to answer this, we'll use the normal distribution and the central limit theorem. So we're going to say, okay, our sampling distribution p hat can be approximated with the normal distribution. The mean is going to be what? 0.5, and our standard error is going to be, 7%. 0.5 times 0.5 divided by the square root of 50. Oh, I say, let's check to use the central limit theorem. Okay, our sample is big enough. N times p is 25, and n times 1 minus p is also 25. Both of those numbers are greater than 10. Our sample is random. And then, the population, there's no population for us to worry about because we're just doing coin flips. All right. So applying the central limit theorem, our mean is p, 0.5, and our standard error is p times n minus p over p times 1 minus p over n in the square root, and that ends up around 7%. And we want to know, okay, what's the probability that p hat is greater than or equal to 60%? So we just do a z-score calculation, okay? our proportion is 60%, the mean is 50%, and our standard deviation is 7%. So I do 0.6 divided by 0.5, 0.6 minus 0.5, take that difference, divide by 0.07, and I get a z-score of 1.41. All right, and now I want to know, okay, what's the area to the right of 1.41? I look that up in the table, and I get just around 8%, 0.0793. So if you flip the coin 50 times, what's the probability you get 60% heads or more? Okay. That's going to happen around 8% of the time. There's around an 8% probability that the coin lands heads, 60% or more. Okay, this is an approximation. It's not the exact answer. It's an approximation because anytime we use the central limit theorem, we're saying we can approximate the sampling distribution with the normal distribution. It's an approximate answer. Maybe. Okay. All right, why don't you guys, let me have you guys try this, okay? So we're gonna say in the population, 42% of people approve of some politician, John Q. Public. And if you ask 80 people, if you get a random sample of 80 people, what's the probability that over half, that 50% or more, actually approve? Okay, so in the population, 42% approve. Well, the question is it possible that you survey, 50 people and then you think over half of them approve? Half or more approve? All right, I'm going to go ahead and pause the recording, and I'll let you work on this. Okay, let's go over the answer to this. All right, so okay, so let's say, so this is what we have. We've got in our thing, it says in the population 42% approve. So our proportion in the population is 0.42. And we're going to select 80 people at random. So I've got n equal to 80. And it asks, what's the proportion that 50, or what is the probability or proportion that 50% or more of people approve of John Q. Public? So we want to know what's the probability that our p hat is going to be greater than or equal to 0.5. Okay, so we'll check kind of the central limit theorem conditions. And so first of all, n times p is going to be 80 times 0.42. Is that greater than 10? And the answer is yes. This is going to be like 33 point something. But hold on, let me go ahead and pull up my calculator. All right, so I got 80 times 0.42. What is that? 33.6. So that's greater than 10. Okay, and then n times 1 minus p is going to be 80 times 0.58, and that's going to be what? 46.4. All right, and that's also greater than or equal to 10. So that's met, and then it's random, and then what's our population? Okay, so as long as our population has more than, population must be over 800 people. So as long as we're not in some tiny town, then this is okay, right? So we'll assume is met. Okay, so I've got that, all of this. So if we assume the population is bigger than 800, then we can do this. Okay, so if this is the case, then we can say our sampling distribution of p hat comes from a normal distribution where the mean is p. The mean is equal to p, and the standard deviation is equal to the square root of p times 1 minus p over n. So, so we're going to have a normal distribution where the mean is equal to 0.42, and the standard deviation, 0.42 times 1 minus 0.42, divided by the square root of 80, or I mean 80, and the square root of that. Let's go ahead and do this. So you have square root of 0.42 times 0.58, 1 minus 0.42, when you divide by 80, I get 0.05518. So that's my standard deviation. Okay, and we want to know, all right, so if this is my normal distribution, we're centered at 0.42. Oh no, what's the probability we're at 50% or higher? My z-score is going to be 0.50 minus 0.42 divided by 0.05518. So what do I get? I get 0.8 divided by this. I get 1.45. I get a z-score of 1.4497, 1.45. Okay. Z-score of 1.45. So now I go to my z table, and I want to know the area to the right of 1.45 or the area to the left of negative 1.45. I get 0.0735. Area to the left of negative 0.1.45. Okay, 0.0735. So this. That's going to be my solution here. Right? So I could do, 1 minus the area to the left of positive 1.45, or I could look up the area to the left of negative 1.45. I get 0.0735. So here we're saying if we select 80 random people from the population, there's around a 7.35% probability that the proportion that approve is going to be 50% or higher. Right? Again, approximate answer, but that's what we're doing with the central limit theorem here. Okay, did you guys get that? Any questions or issues here? All right, let me go ahead and give you your second view quiz answer. Today's second view quiz answer is the letter E. E as in elephant. E as in elephant is your second view quiz answer. E. E. Okay. So we've established this central limit theorem, the sampling distribution. We're saying if you have a proportion in the population P, whenever we take random samples, the random samples, we expect to have sample proportions that follow the normal distribution, centered at P with a standard deviation, so that values close to the population proportion will be high, and as you kind of deviate from that, it becomes a little bit less likely for those solutions to happen, or those proportions to happen. Okay, so we're going to take that and we're going to apply that and kind of form our first bit of statistical inference, and this is going to be the confidence interval. The confidence interval. All right, so the goal when we do statistical inference is we want to make conclusions about the population based on a sample, right? So if we observe a random sample, so what we just did was we said if the population has a certain property, the population proportion is this, what's the probability that our samples look like this, okay? But the goal is to do inference, which is we want to make conclusions about the population. Okay? We want to make conclusions about the population based on a sample. So we're going to say if I select a random sample and I get this information from my sample, what can I say about the population? So we're going to say, let's say I surveyed 100 random people. Okay, I surveyed a sample of 100 random people. And I say, our question is, do you regularly use Netflix? And we'll define using Netflix as you watch Netflix 2 or more times per week. So how many people use Netflix? I don't know. I'm completely making up these numbers. I don't know what actual numbers are for usage, Netflix usage. But let's say 30 people, 30 out of 100 people say, oh yeah, I regularly use Netflix. Okay. So if 30 out of 100 in our sample say they use Netflix, what can we say about the entire population of people? Does that mean in the population, is the proportion also 30% in the population? Is it higher than 30%? Is it less than 30%? What do you guys think? We surveyed 100 random people. In our sample, we got 30%. What does this say about the population? And basically, well, we can't be sure that the population is going to be exactly 30%. But we would expect the population proportion to be kind of close to it, right? I think we would be surprised if it turns out in the population only 5% of people watch Netflix or use Netflix, right? Our sample ended up with 30%. It's a random sample, okay? How could we get 30% if the population is only 5%, right? On the other hand, we would be surprised if the population was 70%, right? How did I end up getting a sample where only 30% ended up? If I have a random sample, how did I end up getting a sample where only 30% of people use Netflix if the true value in the population is 70%, right? So we expect the population proportion to be close to 30%. If the population proportion turns out to be 33%, we go, okay, that makes sense. If the population proportion ends up being like 26%, we go, okay, that's fine. I have no issue with that. Our sample was 30%, and so we're expecting our population proportion to be kind of close to that, not necessarily exactly equal to that. So what we can do is we can say, all right, well, let's create a range or an interval of what we think the population proportion P could be, right? So how do we do that? How do we do that? So put that idea on hold, and I want to give you a silly analogy and draw a picture here. This is the culmination of my artwork ability. And what this is a picture of a dog. Okay, it's a picture of a dog on a football field. The dog is standing on the 30-yard line of the football field. And the owner is also somewhere in this picture too. Okay. The problem is the owner is invisible. The owner is taking the dog for a walk. The leash is also invisible. All right. It's a ridiculous analogy, but just go with it for now. Okay. So we have the dog. We can see the dog. Dog's at the 30. The owner's somewhere in the picture, but the owner is invisible. And the question is, where is the owner? Where is the owner? So what do you guys think? Where do you think the owner is? Is the owner in front of the dog, behind the dog? Is the owner at 31, 26, 29.2? Okay. And the answer is we don't know. We don't know the exact location of the owner. But because we know they're going on a walk together, we can be confident that the owner is close to the dog. Okay? If the dog's at the 30, we can be pretty sure that the owner is not going to be at 70. Okay? There's no 70-yard line. I guess it goes up to the 50 and starts counting it. Yeah, okay. But if the dog's at the 30, we can be pretty sure the owner's not going to be at 10. Okay? So instead of saying, coming to some exact location of the owner, we're going to create a range. Okay, a range. All right, and we know a few things about the behavior of the dog. We know that this dog likes to stay close to the owner. Okay, and there, even though the leash is elastic and stretchy, the dog normally doesn't like to pull hard against the leash. And in fact, we're going to say 68% of the time the dog likes to stay within 1 yard of the owner. 95% of the time the dog likes to stay within 2 yards of the owner. And almost 100%, not 100%, but 99.7% of the time, the dog will stay within 3 yards of the owner. So, stretchy elastic leash, but most of the time the dog likes to stay close to the owner. So, this is the statement that I'm going to make. Because I understand the behavior of the dog, if I see the dog at the 30, I can be 95% confident that the owner's within 2 yards of the dog. I can be 95% confident that the owner's between 28 and 32. Okay? Even though the owner's invisible, I don't know where the owner is, I can be pretty confident that the owner's at between 28 and 32, 95% confident. Okay? Does that make sense as a statement here? All right. So now, is it possible, could the owner be at 32.5? Okay, could the owner be at 33.5? The owner could be. The owner could be more than 2 yards, more than 3 yards away from the dog, okay? That would be surprising to us, though, because that means, you know, if the owner ends up being at 33.5, that means this picture was just taken at one of those very, very rare, not impossible, but very rare moments where the dog chose to be more than 2 yards or more than 3 yards from the owner, right? The dog likes to stay close to the owner, within 2 yards of the owner 95% of the time. But yeah, every now and then, the dog goes more than 2 yards away from the owner, okay? So if the owner if the owner's at 32.5 and we see the dog at 30, that means, you know, the dog was 2.5 yards from the owner, which occasionally does happen, but not very often, and therefore, I think we would be surprised by this result because it means this picture was taken at one of those rare moments. Okay, so why this analogy? Well, this analogy is kind of like making a confidence interval, all right? We are trying, with this dog analogy, we said, I know where the dog is, I want to figure out where the owner is. When we're making a confidence interval, we're saying, I can see my sample proportion. I know the value of the sample proportion, and based on that, I want to try to figure out where the population proportion is. Okay, the population proportion is unknown to us, kind of like the location of the invisible owner. Whereas we are able to see the dog, we are able to see the sample proportion. And because of the central limit theorem that we established earlier today, we can say, well, we know that sample proportions p hat like to stay close to the population proportion p. They follow a normal distribution, okay? If the population has the center at p hat stays within 1 standard error 68% of the time. It's within 2 standard errors 95% of the time. So p hat likes to stay close to p. So, because we know the behavior of p hat, we can be 95% confident that the population proportion p is going to be within 2 standard errors of our sample proportion p hat. Right. So that's the logic that we're using here. We're saying we know sample proportions like to stay close to the population proportion. And therefore, if I see a sample proportion with this value, I can be confident that the population proportion is within 2 standard errors. Okay, so let's make a 95% confidence interval. We're going to say our 95% confidence interval for p hat is I'm going to go basically 2 standard errors below p hat to create a lower bound, and I'm going to go 2 standard errors above p hat to create my upper bound. So like with the dog, we started at 30, I went 2 yards below and 2 yards above, I ended up at 20 and 32. Here we're going to go basically 2 standard errors down and 2 standard errors above. Now, using the number 1.96 gives us more accurate results than using 2. So for tests and exams and everything, your homework, use 1.96. Okay, it's for convenience. We like, about 2 is convenient to think about, but use 1.96. That's going to give you more accurate results. And then one thing is we don't have the population proportion p, so when we use the standard error, calculate the standard error, we use our sample proportion p hat. We plug that in. Okay. That number 1.96 is about 2 standard errors, and that's what we use for 95% confidence interval. That's because we say 95% of the time we're within 2 standard errors, or 1.96 standard errors. We can have different confidence levels. Different confidence levels. We can have a 99% confidence level, a 90%, 80% confidence level. And we do that just by changing the critical value from 1.96, 2.58, 1.645. We just change these critical values here. And these are just the numbers you use. So I would just star these values for the thing is open note, open book, your exams and quizzes, but it'll be handy to have these readily available. So jot them down somewhere else on a note card, or star this page in your notes so you can find this page easily. All right, let's try this out. Okay, so the lower and upper bounds of the confidence interval will be p hat minus z star times, so whatever our critical value is. So if you use something other than 1.96, just plug in z, whatever z from the table is, and then you multiply by your standard error. And so you'll do p hat minus that number and p hat plus that number. Because this part and this part's almost exactly the same, the only difference is the plus versus the minus. Sometimes we just combine it into one formula here, and we say p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. This whole thing, all right, this z star times this part's the standard error. This whole part is known as the margin of error. The plus or minus part, the thing that comes after the plus or minus, that's known as the margin of error. And it's your critical value z times the standard error. All right, so sometimes you see that in like news results. It'll say, so-and-so is polling at 48% approval with a margin of error of 3%. So the real number could, we're pretty sure the real number is anywhere between 48 plus or minus 3%, 45 and 51% or something, right? So that's the margin of error. Okay, so let's revisit our Netflix example, and let's make a 95% confidence interval here. So we said 100 randomly selected people, and then we have 30 people regularly use Netflix. We're going to make a 95% confidence interval, right? All right, so our p hat is our sample proportion. So I take 30 and I divide by our sample size 100. My p hat is 0.3, okay? The 95% confidence interval, the confidence interval formula is p hat plus or minus our z star times the standard error of p hat times 1 minus p hat over n. Is this screen glitching out when I'm writing on here? Or is it working okay? It's like glitching out on me. Okay. All right, well anyway, the z star is 1.96. Okay, so instead of 2, we're going to use 1.96. That's fine. And so if I plug in all of my numbers, I have p hat 0.3 plus or minus 1.96 times the square root of 0.3 times 1 minus 0.3, which is 0.7, over n, which is 100. 0.3 plus or minus. Okay, so now I gotta find my calculator. All right, so I got 1.96 times the square root of 0.3 times 0.7 over 100. Okay, 0.3 plus or minus 0.0898. All right, yeah, let's just call it 9%. Okay, so I'm gonna do so on my lower bound, we'll have well here I'll do the full thing. 0.3 minus 0.0898, and on the upper bound, I've got 0.3 plus 0.0898. Okay, so this becomes 0.3898, or about 39%, 0.39. Okay, and then 0.3 minus this, 0.0898. What is that? 0.2102. Okay, so this 0.2102, so around 21%. All right, so my 95% confidence interval confident that the proportion of Netflix users is between basically 21%, 0.21, and 0.39. Okay, so my sample ended up 30 out of 100 people used Netflix in my sample, and based on that, I'm 95% confident that in the population, the answer is somewhere between, the true value is somewhere between 21 and 39%, 0.21 and 0.39, based on my sample there. All right, I think I wrote this out. So p hat minus 1.96 times all of this gives me 0.2102 and 0.3898. Okay, so I'm 95% confident that the proportion of people who use Netflix in the population is between 21 and 39%. All right, okay. Is that good? Does that kind of make sense? All right, so calculating the confidence interval, I think, is pretty easy. It's just a matter of finding your values and plugging them into the formula. This is the hard part, the interpretations. And on quizzes and exams, I have these, on the quiz you don't have as much multiple choice. Well, I don't know. Okay, you might have some true-false statements. A lot of times these questions trip up students, so pay attention here. All right. So I say I'm 95% confident that the proportion of Netflix users in the population is between 21% and 39%. So I ask, do we have evidence that the population proportion is different from 20%, right? So remember, okay, so here's my confidence interval. I'm going to 0.15. Okay, and then we're going from 21% to right, so we're going from, my confidence interval goes from 21 to 39%. This is my 95% confidence interval. Okay, goes from 0.21 to 0.39. So I'm 95% confident that P, all right, so again, this is the location of our dog, right? And we're saying, okay, I'm 95% confident that the owner, the invisible owner of the dog is between 21 and 39, is basically what I'm saying. I'm confident that P, the unknown population proportion, is somewhere between these two values. So someone says, well, you know, I think the actual value is 20%, okay? Can I say, you know what? I think you're wrong, right? Do we have evidence? You know, my sample, my p hat was 30%. Because my sample is 30%, I make my interval and it goes from 21 to 39%. I'm pretty sure it's not going to be 20%, right? So I could say I have evidence, right? I have evidence that the proportion is different from 20%. 20% is outside of the interval, right? 20% is over here. Okay, p hat 20, could p hat be 20%? And the answer is, I'm pretty sure we are confident that P is not 20% because 0.2 is not inside my interval. Okay. We're confident that the proportion P is not 0.2 because 0.2 is outside the interval. My interval goes from 0.21 to 0.39. 0.2 is outside of that. So I'm confident that it's not going to be 0.2. All right. Okay. So here's another statement. And the phrasing of this one always kind of trips students up. Do we have evidence that the proportion is different from 25%? Okay, so what about 0.25? Could P be 0.25? All right, and here P could be, right? P could be 0.25, all right? 0.25 is inside the interval, okay? Is within the bounds of the interval. Okay, so it is a plausible value. So I could believe you if you say the population proportion is 25%, you happen to get 30%, I'd say, okay, I could believe that. I could believe that. So, but notice what I have to say. Do we have evidence that the proportion, okay, so the question is it different from 25%? And the answer is no, it's not different from 25%. It's not different from 25%. But notice I'm not saying it is 25%, right? So does that mean it's equal to 25%? And the answer here is we can't say that it's equal to 25%. It could be 25%, but is it necessarily equal to 25%? And the answer is no. It's not necessarily equal to, right? So again, if you think about, like, you're seeing the dog at 0.3, is the owner necessarily at 0.25? And the answer is no, I can't be sure that the owner is at 0.25. All I'm saying is I'm pretty sure that the owner is between 0.21 and 0.39, that the owner is not going to be more than, 9 percentage points away from the dog, okay? Or in this case, I'm pretty sure that the population proportion P is between 0.21 and 0.39, but I can't be sure that P is equal to 0.25. Could P be 0.25? Yeah, I could believe that P is 0.25. Could P be 0.2? I'd say I'm pretty sure it's not 0.2, right? 0.2 is kind of far away, so I'm pretty sure it's not going to be 0.2. Could it be 0.25? Yeah, I could believe that. Is it necessarily equal to 0.25? No, we're not comfortable saying that it's definitely equal to some value, right? So the confidence interval will never provide evidence that P is equal to some exact value. So even though 25% is within the bounds of our interval, we can't say that P is equal to 25%. Okay? So I want to make sure that the difference between these two statements is okay with everybody. So we can't say that it's different from 25%, but I can't say that it is 25%. So that's that. All right, what happens if I go from a 95% confidence to a 99% confidence or 90% confidence? Okay, so we want to say, well, okay, well, how confident are you? How confident? What does it mean to be how confident, right? So again, let's say we're trying to catch the invisible owner. Let's say the invisible owner is running from the law, and it's like a cartoon. We're going to throw a net to try to catch the invisible owner, okay? Right, so it's like a cartoon. We're going to throw a net to try to catch the invisible owner. Where do we throw the net? Okay, well, we say, oh, look, we see the dog, and he's taking the dog for a walk. So let's throw a net over the dog. We're going to try to catch, it's like a silly cartoon, right? We're going to try to catch the owner, the invisible owner, by, throwing the net over the dog. And, our first net, I don't know, is this wide, okay? Now, if we want to be more confident that we're going to catch the owner, what do? We should throw a bigger net, right? If we want to be more confident that we're going to catch him, we're going to throw a bigger cartoon net and say, we got you, okay? So if we want to be more confident with the interval we make, we make the interval wider, okay? We're basically casting a larger net, okay? But the thing is narrower intervals are more useful, okay? Narrower intervals are more useful. It's just, it comes at the cost of giving up confidence, right? If you want to cast a smaller net, right? I don't know. If you don't want to cast such a wide net, you need to use a smaller net. But how confident are you that you're going to catch the value inside your net? You're less confident when you throw a smaller net. When you have a smaller interval, you're not going to be as confident. Now, what do I mean by narrower intervals are more useful? Well, let's say somebody says, okay, I want you to plan for a party. How many people do you think are going to show up to this party? Okay? Because I'm going to start making plans. How much food should I order and stuff like that? All right, someone says, oh, you know what? We might get anywhere from 0 to 1,000 people show up to this party, okay? You want me to be 100% confident on my attendance numbers? It's going to be between 0 and 1,000. Okay, well, that's not very helpful. It's very hard to plan a party if the number is going to be between 0 and 1,000, right? How much food do you order if you're going to get somewhere between 0 and 1,000 people showing up? Okay, you can't plan a party that way, right? So a more reasonable thing is you say, okay, well, I think we're going to get somewhere between 200 and 240 people to show up, okay? And then you say, okay, well, now I can figure out how much food to order, okay, at 200, right? But if you have that range, a tighter range, right? If you want even a more narrow range or something like that, then you could end up being wrong, right? It's possible that because you said, okay, let's only plan between 200 and 240 people, it's possible that 245 people show up, okay? It's possible that some number outside of that range shows up. So narrower intervals are more useful as far as using them to make plans and stuff, but but you might be wrong. You might be wrong when you have a narrow interval. Okay, so let's revisit this confidence interval that I made for Netflix. All right, so we said, okay, we made our 95% confidence interval, 30% in our sample, n is 100, okay? And our 95% confidence interval basically is from 21% to 39%. We have a margin of error of around 9%. What happens if I make a 99% confidence interval, okay? With a 99% confidence interval, everything stays exactly the same. My p-hat's the same, it's still 30%, my n is still 100. The only thing that changes is the z, right? 95% my z was 1.96. 99% my z star is 2.58. And that again, that just comes from that one table that I told you to star in your pages. I don't remember. It's like, where is it? This one, okay? So this one, 95% we use 1.96, 99% we use 2.58. So if we do that, the only number that changes goes from 1.96 to 2.58. But that actually affects our confidence interval. Our confidence interval now has a margin of error of 0.118. And my confidence interval goes from around 18% to 42%. All right, so my margin of error is just under 12%. My confidence interval goes, from a touch over 18% to a touch under 42%. So let's just say, so over here it goes from 21 to 39%. Let's just say over here it goes from 18 to 42%. Okay, so let's revisit this question. Do we have evidence that the proportion is different from 20%? Okay, so over here, we'd say, oh, 20% is outside of my interval, right? My interval goes from 21 to 39%. I'd say I have evidence that it's not 20%. 20% is outside of my range. It's not a plausible value. I'm pretty sure, or I'm confident that it's not 20%. Over here, I'm using the exact same data. I just changed my confidence level, and now my interval goes from 18% to 42%. And I say, do I have evidence that P is different from 20%? I'm asking the exact same question, but this time, my answer is no. I'm saying, well, oh, you know what? Look at this. 20% is between the ends of the interval. The interval goes from 18% to 42%, 20% somewhere in between there. So now 20% is considered a plausible value. And I would say, oh, I don't have evidence that it's different from, oh, this is a typo. Sorry, this is a typo. This should say 20%, okay? I don't have evidence that P is a value different from 20%, okay? Same data, same idea of making a confidence interval. The only thing is I changed the confidence level, but now I'm making opposite conclusions. I'm making opposite conclusions. We use the same data. Are these conclusions in conflict? Are they in conflict? Okay, one saying, I have evidence that it's not 20%. The other one saying, oh, I don't have evidence that it's not 20%. So what's going on here? What do you guys think? And the answer is they're not in conflict. The difference comes down to our choice of confidence levels, okay? And you can think of this confidence level business or this confidence level stuff as we can think of this confidence level stuff as kind of like a risk tolerance, okay? Two people can look at the same scenario, right? And and they have the same data available to them, but one person maybe is a little bit more cautious and says, you know what? I'm going to make a different decision, right? Someone is maybe less cautious and they make a different decision, right? So based on our confidence level, what level confidence we want to be, we might end up making different conclusions, right? So the question is, can I eliminate 20% as a possibility is basically what it comes down to, right? Here, my data said I surveyed 100 people, 30% of my sample ends up, use Netflix. And so based on that, can I throw away 20% as a possibility? The one who wants to be extra cautious, right? 99% confident, we want to be really confident before we throw anything away. That person's going to say, you know what? Just to be safe, let's keep 20% as a possibility, right? Just to be safe, it's kind of just like, okay, how many people do you think are going to show up to the party? And we say, you know what, I'm pretty, someone says, I'm 95% confident it's going to be between 200 and 240 people, right? And then someone says, you know what, to me, it's really embarrassing if I don't have enough food. I want to make sure, absolutely, we have enough food for everybody. So do you think 250 people could show up? And someone goes, I'm pretty sure it's not going to be 250 people. How confident are you? Well, I'm 95% confident. Okay, no, I want you to be 99%. Okay, you want me to be 99% confident? Then, yeah, maybe 250 people show up, okay? It's not impossible. It's not a high probability, but it could happen. So the person who wants to be extra cautious will say, all right, let's just go for it, and we'll plan for 250 people because I really don't want to run out of food, or something like that, right? So two people, depending on kind of their risk tolerances, might say, okay, you know what? I'm ready to throw away 20% as a possibility. And someone else might say, yeah, you know what? Let's be safe. Let's still keep 20% as a possibility. And that's the difference between these two confidence intervals. We're using the same data. We end up getting wider intervals if we want to be more confident. And we could end up making different conclusions about certain values. Okay, let me give you your last view quiz answer. Last view quiz answer today is the letter A. A as in apple. A as in apple is your last view quiz answer for today. All right, that's all I have planned for today, for your lecture today. So we'll go ahead and end here. And have a good rest of your day. We'll see you all on Wednesday.